Hello. In this video, we're going to define sequences. We'll give the definition, we'll talk about how sequences are described, and we'll look at the idea of a limit of a sequence. A sequence, sometimes called an infinite sequence, is just a list of real numbers or functions. Usually this list is ordered in the sense that there's a first term of the sequence, a second term, a third term, etc. One example of the sequence is this: the list of numbers 1, 1 half, 1 third, 1 fourth, etc., 1 over k. The dots at the end indicate this goes on forever. And this is an example of a sequence where the kth term is the reciprocal of the positive integer k. We'll sometimes want to describe sequences in a more compact form, so I'll often use notation such as this. And what this means is that we're going to let k take on the values 1, 2, 3, 4, etc. Non-ending. That's the k goes from 1 and then to infinity means we keep going. As we put in the values k equals 1, 2, 3, and 4, we get the sequence elements 1, 1 half, 1 third, 1 fourth, etc. So notation like this is another way to denote a sequence, and it gives us instructions for generating terms of the sequence if we want to do that. Another example of the sequence, very simple one, is the constant sequence. In this case, we just have minus 3, minus 3, minus 3. Every term of the sequence is equal to minus 3. We describe this as minus 3 as k runs from 1 to infinity. And once again, the instructions in here now say when k equals 1, what does minus 3 equal? Well, then it's minus 3. When k equals 2, what's the value of the thing in here? Again, it's minus 3, etc. And that's the sense in which this constant sequence is generated. Now, sequences can be denoted in many ways. For example, we could also denote this sequence by saying it's just minus 3, and we may decide we want the k to run from minus 5 up to infinity. And now when k equals, we start with k equals minus 5. When k equals minus 5, the thing inside here becomes minus 3. And when k equals minus 4, the next one up, we get minus 3 again. When k is minus 3, again, the minus 3 in here doesn't change, etc. So we'll see that there are many ways usually to write a sequence in forms like this. Sometimes you want to change the inside a little bit, sometimes you don't, but certainly we're going to look at sequences that start from many different points. Most of our work will be sequences that are with k equals 1 or maybe k equals 0, but be prepared for others. We can have sequences of functions, and here's an example of that. We see that the sequence can be described as the sign of the quantity j squared times x as j runs from 2 to infinity. So again, when j equals 2, we come up with sine of times x, and so the starting j equals 2 leads to the first term of the sequence, and so forth. So we will use generally the notation a sub k, k runs from 1 to infinity, or just list a1, a2, a3, etc. And in particular, when we want to talk about a general sequence, we'll often talk about just a sequence a1, a2, a3, or b1, b2, b3, b4, etc. And again, as we just mentioned with the minus 3 sequence, there are many, many ways to denote a sequence. So for example, the sequence that we denoted by a sub k, k equals 1 to infinity, could also be denoted by a sub j minus 3, j runs from 4 to infinity. And notice that when j equals 4, we generate the sequence element a sub 4 minus 3, or a sub 1, which again gets us that first term there. J equals 5, we get a sub 5 minus 3, which is a2, the second term, etc. Now, sometimes sequences are defined in a way that's called recursive, so defined recursively, and that means that sometimes you'll need to know earlier terms in a sequence to find the later terms. And a very well-known example of this is the following. Let's take the sequence that's defined as follows. We'll start by defining the first two terms, a0 and a1, as 0 and 1. And for k bigger than or equal to 2, the AK will be found by adding AK minus 1 and AK minus 2. That is the two preceding sequence elements. So with this recipe we have here, we can generate a few terms of the sequence. So again, we're looking at this result. And if we take k to be equal to 2, that's the first k that's allowed in this second part, we have a sub 2, k is 2, equals a sub 2 minus 1 plus a sub 2 minus 0. In other words, a1 plus a0, and those were defined to be 1 and 0, and so a2 turns out to be 1. And you can try this for a couple more. For example, for a sub 3, for example, for a sub 3, up here, we take k equal 3 in this formula, and then the 3 minus 1 turns out to be 2, and the 3 minus 2 turns out to be 1, so a3 is a2 plus a1. We found those earlier. A2 was taken to be 1, and a1 was defined to be 1, and so we get 2. And so each term, in other words, is the sum of the two before it. So 3 comes from 2 plus 1, 5 comes from 3 plus 2, etc. And you might recognize this, of course, as the famous Fibonacci sequence. Now, we're going to be very concerned with limits of sequences. We say that a sequence a sub k, k equals 1 to infinity, converges to a number L if the AKs get closer and closer to a single number L when k gets large. K here takes on only integer values. You want to remember that. And we're going to express this limit then by writing limit as k goes to infinity, AK equals L. So in other words, when k is an integer and k is large, then we're going to have a sub k should be getting close to the number L, so AK approximately L. If the AKs do not get close to a single finite real number, so they approach plus or minus infinity or do not settle down towards a single number, perhaps they oscillate, then we're going to say the sequence diverges and write limit k goes to infinity a sub k does not exist. And sometimes we'll also write or the limit could be equal to infinity or equal to minus infinity if we want to give that extra information about what happens to the terms of the sequence. So we've dealt with limits of this nature before. In particular, we've looked at problems of the form limit as x goes to infinity f of x many times. We saw this when we studied horizontal asymptotes in Calculus 1 and when we studied L'Hopital's rule. And techniques used in evaluating these limits can often be used to evaluate limits of sequences. So we're going to look at a few examples. The first three examples will really be review, because we're going to take a look at limits of sequences using some of the techniques we've seen in earlier courses. So let's start with the following sequence. A sub j, j runs 1 to infinity, defined by 2j cubed minus 4j squared plus 7 over minus 7j cubed plus j minus 5. J runs from 1 to infinity. We'll determine the limit or show that this limit does not exist. So we're going to do here to start, this is a kind of problem we looked at earlier. We often looked at limits of rational functions as the variable approached infinity. This particular example, this quotient is a rational function in J. And we're letting the variable J go to infinity. Our technique in evaluating such limits was to sometimes divide the numerator and denominator by the highest power of j in the denominator. That will be j cubed. And so we've done that in this first step by multiplying the numerator and the denominator by 1 over j cubed. From here on, it's just algebra. If I multiply that 1 over j cubed into each of the numerator and denominator, you can check we get 2 minus 4j plus 7j cubed in the numerator, and minus 7 plus 1 over j squared minus 5 over j cubed in the denominator. As j gets large, all these fractions with j in the denominator go to 0. So we see here, and so the limit turns out to be minus 2/7. And in Calc 1, we would have used this result with x going to infinity and the j's replaced by x to say that the graph of this function has a horizontal asymptote of y equals minus 2/7. So sometimes it can be helpful to look at the graph of a sequence that might, on some cases, give you some information about the limit. But here's what the graph looks like. Remember, for a sequence, we're only interested in integer inputs for the function. So here we've graphed the sequence for j equals 1, 2, 3 up to 20. And each of these dots represents, I'll take the last thing easy to get to. For example, this dot is the point with x coordinate 20. And then the y coordinate is a get by putting j equals 20 into that fraction. And in the next picture, we add the horizontal asymptote, y equals minus 2/7. Remember, the sequence converges to minus 2/7. And in this picture, we can kind of see that as the j's get bigger here, these dots are getting close to the line. Y equals minus 2/7, that is the y values, or a sub j's, are getting close to minus 2/7. Now, as we probably discussed in other courses, keep in mind that using graphs to determine a limit at infinity, that is for large values, is usually not really a good idea. I mean, if the j is going off to infinity, we're interested in really big j values way out here. And so a graph really isn't going to tell you about those big j values. But nonetheless, in a case like this, we can kind of get a feel for the convergence. Next is take a look at the sequence a sub n runs from 1 to infinity, defined by a sub n equals n to the nth over n factorial. We'll determine this limit or show that it does not exist. So once again, what does this all mean? For example, we're going to let n equal 1, 2, 3, etc. And then we're concerned with the values of n to the n over n factorial. So here we'll get 1 to the 1 over 1 factorial, which equals 1. When n equals 2, we'll have 2 to the 2 over 2 factorial. Remember, 2 factorial is 2 times 1. This will give us 2. And then we'll have 3 to the 3 over 3 factorial. That'll give us 27 over 6. 3 factorial, 3 times 2 times 1, or 9/2, etc. So what happens to this sequence a sub n when n gets large? Well, let's take a look at that. I'm going to use kind of a squeeze theorem here of a sort. So for any positive integer n, we have a sub n is n to the nth over n factorial. N to the nth means we're just multiplying n n's together, so n times n times n, etc. Stop when we have n n's lined up. And the factorial means multiply all the positive integers from n down to 1 together. So 1 times 2 times 3, etc. times n minus 1, just before n, and then times n. Now, we're going to split this into some fractions by taking the n over 1 as one fraction, the n over 2 as another, the n over 3, etc. And then write this as n over 1 times n over 2 times n over 3. We'll have a fraction n over n minus 1, and the last fraction here will be n over n. There's n terms in the top of that fraction, n in the bottom, so we can split this up into n fractions. Now, the key here is notice that all of these fractions are bigger than 1, except for the last one, which is just equal to 1. But in particular, if we were to cross out some of these fractions, we'd be getting something that is smaller. Okay? So that's what the next step shows us, is that by noting each of these things is bigger than or equal to 1, that means the whole product is bigger than or equal to 1. So if we were to drop that, cancel that, we get something smaller, n over 1, which equals n. So that tells us a sub n is going to be bigger than or equal to n. And it's actually much bigger than n, but that's enough for our purposes. And we're going to use that then by saying, therefore, we can say the following. We go to take the limit. Limit as n goes to infinity, a sub n. We can then say the following. The limit as n goes to infinity, a sub n, is the limit as n goes to infinity, n to the nth over n factorial. We saw this term was bigger than or equal to n, and so we can get that bigger than the limit of n as n goes to infinity, which is infinity. So therefore, this sequence, the a sub n, given by n to the nth over n factorial, diverges to infinity. And here's what this would look like in a graph. We can see here from the graph that, notice these numbers over here are pretty large, on the order of 10 to the 7th, and we don't get a lot of differentiation in the scale here near the bottom, but we can see that as we move out, these numbers really start to grow pretty rapidly. And again, it is dangerous to say that picture shows that this sequence goes to infinity, but the analysis we already did shows that. For our next example, let's take c sub n to be 1 plus 1 over log n to the log nth power, and we'll define this for n equals 3, 4, 5, etc. We'll find the limit of the sequence or show that the limit does not exist. So for the moment, let's assume the limit does exist and call this L. And so we're going to now take a page from the L'Hopital's rule. We saw that one way to look at limits that involve exponential constructions like this is to take the logarithms of both sides. So if L is this limit as n goes to infinity of 1 plus 1 over log n to the log n, then let's take the log of both sides. So the log of L is equal to the log of this limit. And because log is continuous, we can actually interchange the limit and the log to get this expression. So our log of L is found by taking the limit of the log of 1 plus 1 over log n to the log n. And of course, the reason for using logs is one of the rules of logs says this: if you have an exponential expression inside the logarithm, that exponent can come out in front as a multiplier. And so we do that in the next step. So here's where that multiplier has come down in front. The exponent log n becomes a multiplier, natural log of n outside the logarithm. And then we're going to write this in a form that makes it amenable to L'Hopital's rule. In particular, we're going to rewrite the log n as 1 over log n. So we can check that this expression, after we invert and multiply these fractions, does give us back that expression. And by doing this, now remember when n goes to infinity, log of n goes to infinity. So these 1 over log n's become 0. And that means this expression has in the limit the following form: log of 1 plus 0 over 0. Since log of 1 is 0, that's a 0 over 0 form. And that's one of the forms to which we can use L'Hopital's rule. So we're going to move to a new page, and we're going to apply L'Hopital's rule to this fraction by differentiating the top and the bottom with respect to n. So L'Hopital's rule works like this. Remember, the limit we're trying to evaluate will give us the log of n. There that is. And so according to L'Hopital's rule, because this was a 0 over 0 form, L'Hopital's rule says you can get the limit by taking the derivative of the numerator divided by the derivative of the denominator. So that's what we've indicated here with those derivatives. And we hit the numerator first. The derivative of the logarithm, well, the derivative of the log gives 1 over whatever you're taking the log of. That is this expression, then times the derivative of what's inside that log. Now, we could go ahead and do these derivatives of 1 over log n, but if we work smart, we'd see we really don't have to do that. Here's a very simple next step. The derivative with respect to n of 1, when it's a constant, is 0. So this expression up here really is just the derivative of 1 over log n. And of course, we see that down here. And so I could go ahead and do that differentiation, but I really don't have to because I know whatever happens, those things are going to cancel. And so our limit now, after L'Hopital's rule, has evolved to this. Remember, the log of n goes to infinity. And so that makes this expression go to 1 over 1 plus 0 or 1. So because the log of L is equal to 1, we can then recover L by exponentiation. Log of L equals 1 means L will be e to the L or e to the 1, which turns out to be e. So the limit of this particular sequence turns out to be e. And we can kind of see this, again, illustrated in a graph. Again, remember, graphs are not great ways to evaluate limits of sequences, but they can still be illustrative. Here we've actually plotted the pair n comma 1 plus 1 over log n to the log n for n equals 2, 3, etc., even though we started our problem with 3. And here's what those plots look like. And again, it's not really that impressive. We see these things kind of heading up towards the line y equals e. They really still aren't very close, even by the time n gets out to 20. But if you try comparing large n, like maybe n equals 10,000, something like that, you should see the result getting pretty close to e. The last example contrasts our work with limits of sequences with some of the early limit work we did. So let's consider the sequence. We'll just call it b sub m, for m, say, from -3 to infinity, just to pick a different starting point down there, given by sine of pi times m. M runs from -3 to infinity. So we're going to look at the limit as m goes to infinity b sub m, or the limit as m goes to infinity sine of pi m. And we're going to compare this with the real limit x goes to infinity of sine of pi x. How do these things differ, or do they differ? So the sequence bm first is determined by substituting the integers. We start with -3, then -2, -1, 0, 1, 2. Put those in for the m here. And we find that in each case we get sine of an integer times pi. And for any such integer m, the sign turns out to be 0. So that means this sequence b sub m is really just the 0 sequence. So the sequence b sub m is, with this sine pi m, is just a clever way of writing the 0 sequence. And this is a constant sequence, and so therefore the sequence converges to 0. The limit as m goes to infinity of b sub n, which is 0, turns out to be 0. So this was a very easy sequence limit to evaluate. On the other hand, if we go back to Calc 1, where we talked about limits of this sort, what if we take the limit as x goes to infinity of sine of pi x? It means we're asking about the behavior of sine of pi x when x is a large real number. So now x is not restricted to integers. It takes on any real numbers and we're letting x get very large. Now, what happens in that case? Well, we can get that out of the graph. As the graph below suggests, as we know about the sine function, as we graph sine of pi x, of course, we get this oscillation from 1 to -1, back to 1, etc. And this just keeps going forever. And so as x gets large, this graph never settles down. It repeatedly oscillates through numbers between -1 and 1. So what that means, of course, is that this particular limit for x real does not exist. So here's an example where we see the kind of sometimes subtle difference between a sequence limit and a limit of a real variable as the two go off to infinity. We generally won't have to be too concerned about this, this kind of different behavior happening, but good to be aware of it in case it shows up sometime in your life. Now, finally, let's take a look at here's a table that occurs in your textbook. Most textbooks have a table like this when you look at definitions of limits of sequences. And all this table shows is it supposedly is looking at several limits that might show up, limits of sequences that might show up later in the chapter. So these are good things to keep in mind. Look these over. You can probably think through most of them and kind of see why they make sense. We sort of did this one as our third example, and we looked at something very similar to this one in our second example. So find this table in your book, study it, be aware of these, and again, think about why each of these are true. Okay, so how do we end? Okay, here's what things you want to remember. A sequence is just an unending list of real numbers or functions, usually described by either listing its members, like this, just A1, A2, A3, etc., and then hope there's enough in the pattern there for you to predict what the next elements are going to be and how to write down any element you want. And sometimes we use a more compact notation. In fact, probably use this more than any other because it saves room. Just brackets A sub k, k runs from 1 to infinity. And usually the thing inside here, the A sub k, will be some formula that's used to generate A sub k. You've taken an integer value of k, plug it in for the A sub k formula, and that gives you the value of the sequence. We're going to be most concerned with limits of a sequence. And what we mean by this is kind of an informal definition, but we say that a sequence converges to a real number L, written limit k goes to infinity, A sub k equals L, if ak gets close to the number L and no other number as the integer k gets large. And then again, if no such L exists, or the sequence diverges to plus or minus infinity, we say that the sequence diverges. And again, recall if you saw in the second example, a sequence can diverge to infinity, could also go to minus infinity, and it's possible that it actually never settles down to one particular value, may oscillate between several values, 2 or more, and in any of these cases you'd have a limit not existing. Finally, to investigate the limit of the sequence, we can use many of the tools we learned in Calc 1. These include techniques for finding horizontal asymptotes, and certainly we're going to do a lot with L'Hopital's rule. So read over this chapter. Again, definitions are very important in this subject, so please pay attention to the definitions so you understand what we're talking about when these come up. See you in the next video.